So it's my pleasure to introduce today's speaker, Dr. Mohammad Farazmand. He's an assistant professor in the Department of Mathematics at North Carolina State University. Before joining NC State, he was a postdoc at MIT, and he also did a postdoc at Georgia Tech. He got his PhD in the math department from ETH Zurich. So Mohammad is going to talk about data-driven predictions of dynamical systems from partial observations. Please take it away, Mohammad.
Thank you very much, Sam, for the kind introduction and for the invitation. So the title of my talk is intentionally vague because I'm going to talk about two topics really in this talk. The common theme between them is prediction of dynamical systems from partial observations. When you have sparse observation of a spatial temporal system, how do you make predictions about them? The first part will be about multistable systems, and the focus will be on the importance of the metric that you use in the machine learning compartment of your method. And this is joint work with my PhD student, Brian Chu. And the second part, I'll switch gears a little bit and talk about prediction of rare extreme events, again, from partial observations. This one is joint work with a talented group of REU students who worked with me during summer last year. And also Brian has been involved with this project also. So the general idea of the problem is that the mathematical models that we have for nature are usually continuum models, yet in practice, what we can do is to gather sparse observations of the system. This appears in meteorology, in oceanography, fluid dynamics more generally. To make this a little bit more concrete, the problems that I'm going to look at are problems that are described by some known partial differential equation. It could be potentially nonlinear. U denotes the state of the system, which is a function of x, the spatial coordinate, and time. Just to emphasize that a lot of machine learning methods recently are about learning this differential equation. I assume that I know it and I trust it. So it's not about discovering the governing equations. So these are given, and if the initial condition is known over at least dense enough initial grid, I can, throw it at a numerical integrator and forecast, right? But the issue is that, again, as I mentioned earlier, I only have measurements of the initial condition at the small discrete set of points, which are not dense enough for the numerical integrator to handle it. So the question is, what do you do in that setting? What do you do in that situation? And of course, this is a well-known problem. Data assimilation is the field that deals with that discrepancy. Think of Kalman filters, ensemble Kalman filter, 4D var, especially 4D var tries to reconstruct the whole initial condition on a dense grid from observations on a sparse grid, right? But these methods are usually too expensive to use in real time. Although they are being used in real time, they're not ideal. A second approach that is more recent is to shift the bulk of the computation to offline computation and create a library of offline data that you leverage in order to come up with a machine learning algorithm that then you use in order to do real-time predictions, where the real-time predictions are very fast computations and you can quickly compute things. There is a huge bulk of literature already on this subject. I only list a few out of that big literature here. So here's a picture of how this second approach really works. In the offline computation part, you use your model to create high fidelity model, to create high resolution library of data. These are states of your system sampled from the state space in which the solutions of the PD live in. And then you try to leverage that library together with some post-processing or particularly machine learning algorithm so that you prepare it in a way that when sparse measurements in real time are made, you feed those sparse measurements into this machine learning algorithm, which is pre-trained. And then based on that, you make predictions. Now, this post-processing machine learning part also can inform you in putting your measurements at very special informative locations. In other words, it informs the sensor placement problems as well, and that's denoted by that arrow. So essentially, in a big picture setting, this is the idea that people have pushed forth. And I'll go into more details when we get to multistable systems. But what I particularly would like to emphasize is that in the machine learning compartment, and as a result of that, in the prediction or reconstruction of the system, what usually you need is a measure of similarity between the states in the pre-computed library, offline library, and the states from which in real time you're making measurements. And from that similarity or dissimilarity, your algorithm makes predictions. And that becomes a huge problem when you're dealing with the spatiotemporal systems. For instance, I'm showing you here 3 snapshots of vorticity field of a fluid flow. And if I ask you, based on these 3 snapshots, look at the one on the left and ask you the question, which one on the 2 from the 2 on the right are closest to the one on the left? In the I norm, it's hard to tell. Maybe you want to look at the L2 norm, the difference between pixels, and sum them up, square them and sum them up. But that's not really necessarily a good metric, and usually it leads to bad predictions. So when you're dealing with functions and function spaces, it becomes challenging how to even define a metric that measures similarity between states. So that's one problem, which also, by the way, is well known in computer science community. It's a picture of a famous Swiss roll. If you've done data science, you've seen this before. And it's well known that it's not the best way to measure distance between points in this problem. It's not the Euclidean distance. You want to actually measure distance on the Swiss roll, on the manifold itself. And that's led to diffusion maps and diffusion distance, things like this. The second issue is that whatever metric you come up with, whatever it turns out to be, it better be computable from sparse observations, because again, that's all we have in reality. So these 2 issues are the problems that I would like to address in the first part of the talk. Now, I don't have a universal answer for it. What I can do is in the context of multistable systems, where again, you have a PD of this form, but it has a special structure such that given an initial condition, you may go to asymptotically to different attractors, so different regimes of your system. And given the initial condition, you would like to be able to predict which regime you're going to go to. Here's a cartoon of that. You may have steady states, 1 or more. You can have coexisting chaotic attractors, periodic orbits, quasi-periodic orbits, things like that, that your system converges to. And again, the question is, given just the initial data, can you predict which attractor you will converge to? The offline library in this case would be a bunch of initial conditions that are depicted here by the filled circles that again, these are known on a dense grid. You've evolved them over time. You know which attractor they converge to, and you've labeled them based on the attractor they converge to. So the colors encode the labeling of these initial conditions from the offline library. Now, somebody gives you a new initial state and tells you which attractor will this new initial state, the hollow circle, will go to. And well, I've drawn these lines as the boundaries between basins of attractions to different attractors, which make it easy to tell which attractor it converges to, in this case, to the steady state. But these basins of attraction, we don't know where they are. So if I remove that, now all of a sudden it's a little bit harder to tell from proximity to the labeled data which attractor this initial data will converge to. Another point that I want to emphasize again is that in this new data, which you want to classify, this is a supervised classification problem, basically, right? That you want to classify, this is not known over the entire spatial domain. It is known only on a sparse grid, right? So this is the second challenge. First, how do I measure distances? Second, is it computable from sparse measurements? Well, let me make this a little bit more concrete, but by giving you an example of such systems. We have a few examples in our paper that I refer you to if you're more interested in all the examples. I'll focus on this reaction diffusion equation, which this is the reaction part, and the diffusion part has a weight in it, which is a function of space. Usually it's a constant. If it's a constant, you get the usual diffusion term. But in order to make the problem a little bit more interesting, we use the non-constant weight. We used Neumann boundary conditions, and U is the state of the system. It turns out that with the weight that we picked, you have 4 options in terms of the attractors you converge to. A1 and A2, which are also present when you have a constant weight, but this non-constant weight, it creates 2 more attractors, A3 and A4. On the left, top left here, you see the library of the initial conditions that we've evolved and colored them based on the attractor that they converge to. So this is the offline high fidelity, high resolution library that we have. And they are labeled, let's say we have M initial conditions in there, and they labeled according to the attractor they converge to. The classification problem is that a new state is given, which attractor does this new state converge to? And that basically is the statement of the problem. As I mentioned, usually the way you want to do this is that you take the new state and you measure its distance from all the labeled states, and you say, well, it's closest to this labeled state in some sense, therefore it converges to the same attractor that the closest labeled state converged to. But again, measuring that distance is not straightforward in these kinds of problems. Usual go-to metric is the L2 norm, but as I mentioned earlier, usually it leads to very bad predictions, and I'll show you with examples in a second. Some PDEs have an intrinsic norm that comes with them. Sometimes they have a variational structure that really dictates the norm that you have to pick to be consistent with the PDE. In fact, the reaction diffusion equation that I showed does have an intrinsic norm and a variational formulation, but I won't go into the details of that. But usually these intrinsic norms are not available. Very specific PDEs have them, but even when they are, you still need dense measurements in order to evaluate them. They're not good for working with sparse measurements. So what we are proposing is to use this offline library of labeled data in order to learn the norm from the simulation data that you have, and then use that norm in practice. And the 2 guiding principles that we use are one, that the metric has to be consistent with the data, by which I mean that initial conditions that converge to the same attractor should be relatively close if measured in that metric. The second requirement is that, again, the metric has to be computable from sparse measurements, because in real life, that's all we have, right? So with these 2 guiding principles in mind, let me tell you about the algorithm that we propose. In order to do that, I have to define a couple of things. First, we define a similar set, which is a pair of initial conditions that converge asymptotically to the same attractor. And then the dissimilar set, which does the opposite, pairs of initial states that converge to different attractors. And among all the functional norms that exist in functional analysis of PDEs, we restrict our attention to these types of weighted L2 norms, where phi is the weight and is unknown, and we would like to learn that weight. The way we learn that is through the sparsity-promoting metric learning, which was inspired by the work of Michael Jordan's group at Berkeley. They did this for finite dimensional problems, and they didn't have the sparsity-promoting part that turns out to be crucial for our purposes. I'll get to the differences in more detail in a second. So let's look at this constraint optimization problem. Forget about the part in red for a second. I'll come back to that. What is this part is trying to do in blue is trying to say that sets that converge to the same attractor, meaning that they're in the similar set, they have to be close in some sense. So this minimizes the sum of the distances between pairs like this, right? Now, if you don't put any constraint on this optimization problem, it gives you a trivial solution where phi is just 0. Every distance between any 2 points or data points are 0, not very useful. Therefore, we put constraints on it that enforces that the sum of pairwise distances between states in the dissimilar set has to be larger than equal to a constant. Now, this constant, we've put it equal to 1, but it turns out that it's this optimization problem has the scale invariance property. That meaning that if you put a 2 here, this phi just gets uniformly divided by 2. So it doesn't really matter what you put there. So normalize that constant to 1. And the second constraint is that phi has to be non-negative for the metric to be a metric, right? To be well defined. Now, The most important part is this elastic net penalization that we add to this minimization problem, which the first part of it is the L1 norm of the weight. And this enforces, as lambda increases, it enforces that the phi has to be non-zero at a minimal number of points. Now, the L2 part of the minimization problem is a little bit technical. I won't go into details of it, but if you ask me, I can explain further later. But basically, let me just say that it makes the optimization problem well posed. Without this part, there are some quirky properties of the optimization problem that this L2 part gets rid of. So we use this form, but the most important part of the penalization that you should focus on is this sparsity promoting part that is crucial.
Mohammad, can I ask you something? What is the range of lambda here? Is it
between 0 and 1?
Between 0 and 1. Okay, yeah. Right, thank you.
And alpha is a positive constant. Thanks for asking. Good question. Right. So you want to solve this optimization problem over all pairs of data from the offline computed library, right? So the algorithm is basically like this: generate initial conditions or sample them as you wish, evolve these initial conditions under the PD and label them according to the attractor they converge to, then solve this sparsity promoting optimization problem to find phi, the optimal norm that comes into that metric. Now, these 3 steps are computationally expensive, but you do these once and offline, and you never do it in real time anymore, right? So you do these, and then in real time, what you do is that you use measurements that are available to you and measure distance between the new state to the library that you've already calculated within that metric that you have learned from the 3rd step. And based on that, you do classification or clustering of your new initial condition. This is pretty cheap and very quick, and you can do that in real time from sparse observations. So let me show you the weights for corresponding to the reaction diffusion equation. For lambda equals 0, where we have no sparsity promotion, you get weights which are 0 in the middle of the domain, indicating that whatever happens to your solution, initial conditions in the middle of the domain is really not important in terms of where they asymptotically go to. But then when you get closer to the boundaries, it becomes more important. Yet for lambda equals 0, that blue curve, you see that you still need a dense grid near the boundaries where the weight is non-zero in order to calculate the metric. But as you increase the sparsity promotion parameter, you turn that knob on, you see that the metric gets more and more localized around 2 points here and here. This is corresponding to 10 labeled data. If in your offline library you only have 10 initial conditions, it's a similar story. It focuses, in other words, around the same point if you have more labeled data, like 20 labeled data. And these points turn out to be around plus minus 0.72, right? We don't decide where these points have to be. It just comes out of the optimization problem that the sparsity promoting metric focuses around these 2 points. So to recoup, increasing sparsity promotion concentrates the weights around 2 points. Might be more points, but this particular problem is just 2 points. Automatically, in other words, it's telling you that these 2 points are very important for you. You have to make measurements in these 2 points. So automatically identifies this optimal sensor locations. It's giving you the indication that you should be making measurements at these 2 points. You can go further and say, well, let's take this to its logical conclusion. Since it's concentrating around these 2 points, let's just make up a weight, which is the delta function at these 2 points, right? Once you make that generalization, then you're able to really evaluate the metric from these 2-point measurements that at x0 and minus x0, with x0 being 0.72. Right? Now, here are the results you get in terms of the classification error as a number of labeled data in your library, offline library. First of all, there are different norms showing here. Well, the first one is the dash black one, which is if you just were to use the L2 norm, right? As I mentioned, this PD has an intrinsic norm, and the classification error for that is shown in purple. And then finally, what happens if you do these two measurements coming out of the SPML algorithm, make measurements there and make predictions based on these 2-point measurements, right? It turns out that these 2-point measurements miraculously outperform L2, not that surprising, outperform the intrinsic norm also of the PDE. And they are computable from sparse measurements, just 2-point measurements. And they emphasize again that we don't decide what these 2 points have to be, it comes out of the optimization problem. Question, what if I take 2 different points that are different from these 2 points that SPML told us are important? Here are the results you get. If I put at 1 and -1, my measurements, or plus minus 0.5, you see that you uniformly get larger prediction errors from those other 2-point measurements. And so you consistently do better from these optimally placed sensors coming out of SPML. So to conclude this part of the talk, let me just reiterate that in problems that when you're dealing with spatio-temporal systems, PDs namely, it's very hard and very important what kind of metric you use in order to assess similarity and dissimilarity of the states. We propose sparsity-promoting metric learning, SPML, as a method to discover this metric from simulation data. And once you have that metric, you can classify based on sparse measurements. And the two really important things that went into principles that went into setting up this optimization problem is consistency with the simulation data and computability from sparse observations. And I showed you an example with a reaction diffusion equation, which from 2-point measurements, we can make predictions with larger than 90, actually it was 95%, it should have been 95% accuracy. As I mentioned earlier, there are more examples in our paper that I would refer you to that. Now let me switch gears and talk about the problem of extreme events, but maybe it's a good time to pause here and see if there are any questions so far.
I would have a question if possible.
Yes, go ahead, Savis.
Oh,
thank you.
Good.
Hi, Mohammed. Thank you. That was very interesting and clear. So I have 2 questions on that first part. First is when you do the online classification, once you have learned the appropriate norm, how do you do that? Do you rely on some K nearest neighbor sort of algorithm? Yeah,
so the results that I showed you on, let me see which slide. These are from just the dumbest thing you can do, which is just the nearest neighbor.
Okay.
You can do more sophisticated things, K nearest neighbor, once you have the metric. You can do spectral clustering, but in your spectral clustering, you don't do the Gaussian kernel, you use this metric. You can do all.
Okay, that makes sense, yeah. And so I really like this idea of having a properly tailored norm to measure distances. And have you thought if you can apply these ideas to the standard filtering problem where you're trying to just reconstruct the high-dimensional states given sparse observations at a given time instant, which is a different problem from the one you're looking at, but maybe similar ideas could apply.
Right. Thanks. This is a great question. So the filtering problem, we have thought about it, but haven't made great strides on it, to be honest with you. I mean, as you mentioned, it becomes a more challenging problem if you want to. So in other words, it's a great question because I forgot to emphasize this. What we're doing is really classification in the sense that you don't care about the dynamics of your system in between the initial condition and the asymptotic, right? I can't tell you anything about what happens in between. I can predict very accurately where it will end up, but I can't tell you anything about the dynamics in the middle. Now, if you wanted to know the dynamics in the meantime or reconstruct the initial condition, it becomes a much more challenging problem.
Yeah, thank you.
Can I ask you, so this inner product, you actually have an inner product space here, right? But it's a valid inner product. Does that have any other utility than just the norm? Like, does the angle between two different vectors, like can you use this norm that you've learned in other ways as well, other than this application? Have you thought about that?
That's a great question that I had not thought about. If you have an application in mind where the inner product is useful, I'm sure this can be also applied. But
yeah, to me, this looks like for bifurcating systems. If you want to effectively, if you do any kind of reduce normal, you need a projection, you need inner product. I wonder.
Oh, I see. Yeah.
Because that's a non-trivial choice, how to find the inner product, and this sounds very interesting.
Yeah, great point. Yeah, no, absolutely.
Okay. All right. Any other question for Mohammad? All right.
Now you mentioned this, like, it just occurring to me that this algorithm DIME, which people use for construction, definitely does need a projection, right?
That's right. So it does need projection. I mean, I see a lot of interesting stuff. That can be done here. Yeah. All right.
Okay, if there are no other questions, maybe let me move to the second part of the talk, which is about the extreme events, which are more and more these days. And these events obviously cause, billions of dollars in financial damage, death, displacement of populations, erosion to the environment. So we're very interested generally in my group in predicting these in real time, quantifying them over a long time, meaning that you don't predict individual events, but you want to know what is the probability over 100 years, for instance, in long term of one of these extreme events taking place. And mitigation of them, can you do anything about mitigating? Usually these are, undesirable events, so you want to be able to control them if possible. And also sometimes even the mechanism that causes these extreme events are not very well understood. And so you want to ask the question, are these, what is the mechanism that causes them? What I want to talk about today, though, is the focus on real-time prediction of them. I will not touch on the other aspects of extreme events. By real-time prediction, I mean in real time, can you tell if there's an upcoming extreme event in a near future? Let me motivate this by showing you a video. I apologize for the grainy quality of this video. Obviously, US Navy doesn't get enough funding for better cameras. But what you're going to see basically is an aircraft carrier, an aircraft on an aircraft carrier somewhere in the middle of the ocean. And you'll see the aircraft going down the runway, and pay attention to what happens right before it takes off. See that a huge wave all of a sudden hits the ship and the aircraft. And if you keep watching, miraculously, the pilot is so skilled that manages to control the aircraft and flies off. It doesn't sink. But there has been instances where these aircrafts have sunk because of the wave. The other thing to mention about this video is that there is anecdotal evidence from people on board the ship that day that you can also kind of see in the footage that the sea wasn't nice. The weather was nice. The sea wasn't stormy or anything like this, which brings the point that people already know that these extreme waves or rogue waves can come out of nowhere on a nice sunny day and hit you. And this is actually a common property of extreme events, by which I mean that they can occur spontaneously with very little early warning signs, at least obvious early warning signs. And that makes their real-time predictions really, really hard. So we're interested to nonetheless see if we can do prediction of them. The other thing that makes them difficult is what I already mentioned, that usually we don't have good enough measurement resolutions in order to use our continuum models to make predictions. But even there is an added level of difficulty, and it has to do with the small data problem. Extreme events are also rare. For instance, these rogue waves, people have documented them for centuries in their logbooks. Sailors have written about them, but nobody believed them because they're so rare that a sailor could go to the ocean for a career and never see them. So they rarely take place. And as a result of that, you can have a lot of observational data, over even like decades of observational data, but only a very small portion of this observational data corresponds to these extreme events, rogue waves in particular, and other types of extreme events as well. So again, you can have large amounts of data, but really when it comes to extreme events, you don't have much data. So the framework that we're proposing in the second paper that I'm going to discuss is the following: to again leverage offline numerical simulations. You assume you have a model that you trust. You run it for as long as you want, because these are being done offline. And you collect data, the full state of the system. And then from that, you subsample, so that all you really use to give to feed into your neural network are the quantities, our number of quantities that you actually can measure in real life as well, right? So you form these from your simulations and use these as input data, train a neural network which predicts some quantity of interest. The quantity of interest here would be the sea surface height in the case of rogue waves, for instance, right? Near your aircraft carrier. Tau here is the prediction time, how much in the future you would like to predict them. And once you've done this step offline, again, costly, it involves large amounts of numerical simulations and on the top of that training a neural net. But then once you've done this offline, you have a pre-trained neural net, you have your experiments or observations, which are consistent with the input data that you use to train your neural net to begin with. So you just feed it into a neural net and you make predictions about the future of the quantity of interest Q that you're interested in. So we wanted to basically examine the feasibility of this framework. And the questions that we were particularly interested in is, first of all, can you accurately predict upcoming extreme events in this framework? How sensitive to noise are the predictions? Because again, numerical simulations have minimal noise in them, a round of errors and discretization noise, but that said, it's usually negligible. But real-time observations are always polluted with a lot of noise. So once you add noise, what happens to the predictions? Sensitivity to hyperparameters of your networks. Do you have to really fine-tune your network for it to work well, or it not? With little effort, you can train a reasonable neural network. Reproducibility of the neural nets, meaning that if I retrain my neural net, will I always get more or less the same accuracy of prediction, reliability of prediction? And finally, the sensitivity to the input data, because if I go back to the previous slide, I pick a bunch of observables that I feed into my neural net in order to train it. How sensitive is the prediction at the end to the type of data that I feed in? Are there some set of data that would outperform another set of data? So there are a lot of questions that we explored in this paper, and I refer you to the paper for a detailed discussion on this, but I particularly would like to focus on sensitivity to noise in this talk and sensitivity to the input data, although I will touch on the other three as well. So we did a very thorough analysis or study of this. We took 3 dynamical systems in the increasing order of complexity, from the Rossler system, which is a low-dimensional ODE system. Its attractor looks like this. There were 2 time series that we picked as inputs, and quantity of interest I will come to on the next slide. I will come back to this and tell you what the quantity of interest is. A FitzHugh-Nagumo system, which is a higher dimensional system of coupled oscillators. Still, we use just 2 time series as input. And finally, a PDE, Kolmogorov flow, which is a special type of fluid flow, where we use potentially more observables, up to 9 observables, and a quantity of interest that I will again discuss in a second. By the way, the horizontal lines here are a threshold that if your quantity of interest exceeds that threshold, you declare an extreme event has taken place. And this threshold usually is up to the practitioner in the field, what this threshold should be. But we also vary that threshold and quantify the accuracy of our predictions as a function of that threshold. Again, I will come back in more detail to that as well. And we also picked 3 different neural networks: feedforward, LSTM, long short-term memory, and reservoir computers. So in total, we have 9 combinations, right? 3 systems and 3 different networks. Let me now tell you a little bit more about the systems. Rossler, as I said, is a simple three-dimensional system. The quantity of interest here is the third component, x3, and the inputs were just x1 and x2, the inputs to the network. FitzHugh-Nagumo is much higher dimensional. It's, as I said, a system of coupled oscillators. It's nonlinear. The number n here is the number of oscillators, which we chose to be 100. So 200, because there are two equations, 200 equations, 200 dimensional dynamical systems. And the quantity of interest here is the average of the VI components. As you see, once in a while, this is the VI components, once in a while, they all synchronize and make this average large, and you get one of these extreme events once in a while. Again, rare, but they do happen. Kolmogorov flow, which is Navier-Stokes, and the quantity of interest here is the energy dissipation rate. Now, these three systems, one last thing I want to say about them is that they all have these extreme events. For X3, is these bursts of, for Rossler, is the bursts of X3 component that take place. And it has to do with a homoclinic cycle, which is embedded into this, this attractor. The second one has a very different mechanism. It's synchronization. Synchronization in the system leads to extreme events. The last one, it is more complicated how the extreme events take place, but it essentially has to do with nonlinear energy transfers within the system that trigger the extreme events in this turbulent flow. Point being that there are three systems with three distinct mechanisms for formation of extreme events, but our approach is agnostic to the mechanisms. It doesn't care. It says, give me an input. I don't care what the mechanism, I'll do my best to make predictions of extreme events. The next thing that I want to emphasize, it has to do with the type of input data, type of observable. In particular, for the turbulent flow, what I will show you in the results in a second, I'll show you two types of observables. Let me focus first on the right-hand side. One type is just samples of vorticity field of the system sampled at 9 arbitrary points. So I have 9 time series vorticity measured at those 9 points. The other one type of observational input data is the real and imaginary parts of a very particular Fourier mode of the system. Now, this is a very weird, admittedly observable, but we had a previous study that showed that actually this Fourier mode plays a crucial role for these extreme events. In fact, energy transfers from this Fourier mode to the mean flow trigger extreme events in this system. That we just didn't discover through machine learning, discovered through a good deal of analysis. But now that we have that information, let's see how machine learning would do if we feed it with these types of observables. Here's a slide which contains too much information, but I try to summarize the main points. So we have 4 columns: Rossler, FitzHugh-Nagumo system, and 2 for Kolmogorov. 1 with input data being the Fourier modes, the last column being the input data with vorticity measurements. What I show here is, on the first row, is the precision recall curve, which is a standard technique for measuring the accuracy of extreme event or rare event predictions. Basically, what it is, it quantifies, I won't go into details of it, but what it quantifies is how many false negative and false positive predictions you've made. The closer these curves are to 1, the better your predictions are. In other words, the larger the area under the curve, the better your predictions are. And you see that for Rossler, all of them do reasonably well. FitzHugh-Nagumo, similarly, the reservoir computing does slightly worse than LSTM and feedforward, but it's reasonably well. With Kolmogorov flow with Fourier modes, it does reasonably well, but with vorticity, it doesn't do that well, as you see. The second row is what you usually show in machine learning papers, which is the normalized RMSE, the root mean square error. And you see that they're comparable for different systems. Reservoir computing RMSE is a little larger and so on and so forth. Depending on the system, it could be different. It's really the combination of which architecture you use for which system is kind of not clear here, right? For some systems, reservoir computing does better. For the other ones, feedforward does better, right? But the important point about this row is these little error bars that you barely see. Some of them are larger, but all these dots have error bars. Some of them are so tiny you don't see. So what they correspond to is the retraining of the network. So we retrained our networks many times and then measured the corresponding errors. And you see that these errors are very small, which basically is telling you that these trainings, these predictions are very robust under retraining. In other words, the optimization part of the machine learning is doing a great job. It's always converging more or less to the same minimizer. And finally, the scatter plots are shown on the bottom row, where they show the predicted value versus the true value of the quantity of interest. For Rossler, it's almost perfect. FitzHugh-Nagumo, less so, but still pretty good. For Kolmogorov, I want to focus now on these two columns. For the Kolmogorov, if you use the Fourier modes as the input, it does pretty good. It's near close to the x equal y axis, right? So these are extreme events that correctly were predicted. These are extreme events that, non-extreme events that were also correctly predicted, and false positive, false negatives in the other two quadrants, which are very little of them in those quadrants. But if you use vorticity as input, here I have only, when I use Fourier modes, I have only 2 time series as input. For vorticity, I have 9. I have more time series as input, but it does much worse compared to the Fourier mode, which basically the takeaway is that the type of input data that you feed into your neural net for these predictions, at least for these purposes of predicting extreme events, is very important. It can play a crucial role in the accuracy of the predictions. And if you can do some work ahead of time to figure out the right types of observables to measure, it will make a big difference. Next thing that I want to say is about how many experiments. So remember that my training is done on simulation data that it can, in principle, run indefinitely, right? So how long should these simulations run for? In other words, how many extreme events do I need before I say, okay, it's enough, I can now train my neural net? Well, a priori, again, it's an interesting mathematical question, if you will, but a priori, we don't know. We don't have a good answer to that. But what we did is to just run it for a long time and see, based on how many extreme events in our training data we had, see what the accuracies were. Here is this area under curve, which is the area under the precision recall curve, and recall that, remember that if that is closer to 1, better predictions you're making. So in this, I think this corresponds to the Rossler system, but it's a similar picture for other systems as well. The more and more obviously extreme events you have in your training data, you get better predictions, but at some point it plateaus, right? And it stays very close to 1, at which point you say, well, that is enough, probably I can stop here. Now I show you this because we did this training without doing anything really creative. We chose, the standard architectures of whatever neural net we were using, and the loss function is the usual L2 error loss function. Now, there are some recent studies that come up with clever ways of defining a loss function which is claimed to be more appropriate for prediction of extreme events. And it has to do with the fact that, again, if you're only relying on observational data, it will not have enough extreme events for training. So they come up with these clever loss functions, which kind of weights the extreme events more than the rest of your data. Essentially, that's what it's doing. And it is necessary. These loss functions actually do somewhat improve the predictions if all you have are these observational data. But if you have a model, in our case, where you can run it indefinitely, you don't really need to use these special loss functions or a special architecture for your network. Just use the straightforward thing. Just make sure that you have enough data, in other words, for it to converge to some AUC, which is acceptable.
Can I ask you something, Mohammad?
Yes.
Can you use the previous algorithm in the first part of the talk to find where you need to wait for the extreme events to find the loss function?
Yeah, yes, good, very, very good question. In principle, well, where to wait for the loss function? Let me answer the question first in the way I first understood it. Can you use that in order to learn where to put your sensors?
Exactly.
Yes, you can use that, yes. And it actually, we have work in progress that is
right, because that's like a density, basically, that phi of x that you find, right? So
right,
like
but the density you want in these specialized loss functions is a density not in space, but a density over the samples of the snapshots of the system.
That's right, yes, right.
The different types of density. Right?
Yep. Okay.
but great question. Yeah. And finally, what I want to say is something about the robustness to noise. So initially, when we were doing this work, we said, well, we have the simulation data that we can use for training. And this picture that I'm showing you is basically using the simulation data as the numerical algorithm produces it and feeding it into the neural net in order to train it. And then we said, well, observations, though, always have noise. So what we did is to add noise to the testing data, not the training data, but to the testing data, we added artificial noise to see how it persists under noise. And as you would expect, as you increase the noise intensity, the accuracy of the predictions deteriorate. However, there are some systems, and what was interesting to us at least, that for FitzHugh-Nagumo system, it deteriorated very rapidly. Even with 5% noise for feedforward, for instance, the accuracy was really bad, similarly for reservoir computing and LSTMs. So what we did next is to actually pollute our training data, which again comes from simulations, and it's not necessarily polluted, but just artificially polluted with some data as well. And that greatly improved the predictions. So here is the time series of the true data, true quantity of interest in blue, and the time series of the neural net predictions in orange. In the case where we have no noise added to the training data, and you see that is way off from the reality, right? Hence these very small accuracy plots. But then if you go take your training data and add 20% artificial noise to it, all of a sudden the same neural network with the same architecture does very well in predicting the time series, right? And here are how, as you increase the noise intensity in the testing data, how the accuracies change. And you see that compared this to that, you see it stays close to 1, even with 20% noise added to the testing data. I want to emphasize that in the training data, we just once added 20% noise, didn't change it anymore, trained, but in the testing data, we gradually increased the noise intensity. And it worked uniformly well under all this testing. It basically tells you that don't train on clean data, add some noise. And that has to do, it's not that surprising in retrospect, it has to do with the fact that if you use clean data, the neural net overfits, basically. Overfits to the clean data, and when you have noise, which puts you in an out of sample situation, then it can't perform that well.
Mohammad, did you add white noise to corrupt this?
Yes.
Okay.
Yes.
And not colored noise?
We didn't try colored noise. Should we expect very different outcomes?
No, I was just guessing because yeah.
Okay. No, we just added white noise. Yeah.
Okay.
All right, just to conclude, running out of time here. So the answer to the second part of the question is that no one size fits all in the following sense, that there is no, if you give me a dynamical system, I can't tell you a priori what architecture is best. LSTM, reservoir computing, feed forward to use with that system. Again, a very interesting research question. Are there properties of dynamical systems that make one dynamical system more suitable for LSTMs compared to another dynamical system for feed forward? I don't know the answer to that, but it's a very good question to investigate, in my opinion. Yet, there are some broad conclusions that we were able to reach. One is the robustness to noise. To address that question, LSTMs across the board seem most robust to noise to us, even with 20%. That previous slide that I showed you, these are LSTM. You see the LSTM results are closer to 1 than the other 2. And it's true for other systems as well. So they seem to be most robust to us. Do we need a lot of fine-tuning of parameters? In case of feed-forward networks, we did. In case of LSTM and LSTMs, not really. Very little fine-tuning was required, or if any. Reservoir computing, how you choose your density of the reservoir and things played the marginal role in determining the accuracy of the predictions, but again, it wasn't too bad in the sense of you have to spend, a lot of time fine-tuning your reservoir computers. Reproducibility was good across all different neural network architectures, which again means that stochastic gradient descent that is used in the in the optimization part of the neural net is doing a pretty good, consistent job. Most important thing that we discovered is that the sensitivity to input data, type of input data that you feed in, really plays a very important role in the kind of predictions you make. In principle, neural nets come from universal approximation theorem, so you think any data can fit to any data. But in our experience, the input that you give in case of at least predicting extreme events in these systems is crucial. It makes a huge difference in accuracy of predictions. The last thing that I already mentioned is that if you have enough simulation data, you don't really need to worry about the special architecture that is better suited for extreme events or a special loss function that is better suited for extreme events. If you have enough simulation data, you can pretty much use the standard boilerplate kind of neural networks and training. All right, with that, let me just stop and thank you again for your attention, and I'd be happy to answer questions.
Thank you, Mohammad, for an excellent talk. I really enjoyed it. I have questions, but I want to see if the audience has questions for you. So please, if you have questions, just unmute and ask.
So I would have another question.
Oh yeah, go ahead, Savis.
Thank you. So again, very interesting. So I had a question regarding the noise part.
Mm-hmm.
So you showed that if you add the same amount of noise in your training data as you have in your testing data, then it performs well. So I was wondering if, for instance, you have more noise in your testing data than in the training data than the testing data.
Oh, okay.
Do you keep good results there?
Right. So yeah, I didn't explain this well then, because actually this is the case here. So this is the same training data with 20% noise added. And then the testing data has 0 noise or more.
Okay. Oh, yes, it's my bad. Yeah. All right.
It goes pretty well. Yeah.
Yes. Okay.
Again, I don't claim to understand it. I didn't expect it to. I thought if you add 10% noise to training, it will perform on 10% noise on test data. But like 20% works well across the board. I can't really explain this. If somebody knows more about why it's working across various testing data noise, I would be very interested to hear that.
Yeah, that's very interesting result, no? Because usually neural networks are known to be very sensitive to the amount of noise.
Yeah.
And it's doing better for no noise, actually, right? So when
no noise in the testing.
In the testing, right?
You definitely do want noise in the training.
For the training, absolutely. Yeah. Okay, yeah, very interesting. All right, any other question for Mohammad? So I do have a question. So one of the main conclusion of the second part was that what to measure, right? So the input, right? So, and if we measure different components of this in the state vector, and it changes in time, basically, right? Not fixed locations, locations that do because I don't know if you want to measure the same point, or it must be the optimal measurements would be time dependent as well, right? So but that may not be appropriate for training a neural. I just don't know how that would work. That's my question to you. If the input location, like you're measuring different components of the state vector, and those components are changing in time, can you still use this training framework?
We haven't tried it. In principle, you can just use it. Yeah, it again doesn't care where the time series
exactly
comes from. And see, it would be an interesting question to investigate. And sometimes, as you well know, it's really you don't have a choice. The sensors are moving around.
Exactly. Yeah.
Like buoys in the ocean, they just move with the flow. Exactly. And they're measuring. So yeah, it's an interesting question, but we did not investigate that part of it. And then the other question is, which I don't have an answer to, what is the optimal path the sensor should take for
okay
information?
That's exactly right. So
in some problems it's kind of obvious, like shock formation, right? You want to go with the shock, where the shock would potentially form, things like that. But generally speaking, I'm not aware of a good way of doing doing this.
But do you think there is something fundamentally wrong with training a neural network when the input measurements are changing in time? Like, or
I can't think of a fundamental problem. No.
Yeah, okay. So you think, let's try and see what happens if you have an algorithm to find like a time-dependent points as the input.
Yeah.
Okay. Yeah, that's very interesting. Very interesting. Fascinating. Okay. Any other question for Mohammad?
In fact, actually, maybe make one more comment about this. In the first part of the talk, where I was saying about reaction diffusion, we did try moving sensors to see
exactly
if they would outperform these two points that were discovered from the SPML. And it turned out, no, actually fixed measurements would be better. But this is a very special problem. I can't generalize that beyond this particular system.
I see. Yeah. Okay. Yeah, very interesting. All right. If there is no more question for Mohammad, I want to thank you again. That was an excellent talk. I learned a lot and appreciate
thank you so much.
Yeah,
thanks again for the invitation.
Of course. Yeah. Thank you.